Hi, I'm Paul. We're doing a walkthrough of an ACT science practice test. Normally you'd have 35 minutes to do 40 questions. Directions are there are several passages in this section, each of which is followed by questions. After reviewing a passage, choose the best answer to each question. Refer back to the passages as often as you need. Calculators are not permitted on this test. Okay, well, before we get started, what can we say in general about the ACT science? It's at the end of the test, so you will not be at your freshest mentally, possibly. Although there is a break in the middle of the test. You get 35 minutes. There will be 6 passages, maybe 7. You'll get 2 or 3 data representation questions. You'll get 3 research summaries. You'll get 1 conflicting viewpoint. The questions tend to get harder as you go through each section. And the passages themselves may get a little harder as you go through. Let's talk about some good ways to waste time on the science portion. One would be reading more of the passage than you need to. It's probably a good idea to look at graphs, maps, whatever you're given, the visual stuff first, and then read as needed. Definitely don't try to read the passage the way you would read a science passage if you were studying for a closed book science test. The information will always be there if you need to go back and refer to it. Let's see. Take a little bit of time, 30 to 90 seconds probably, to get organized before going into the question. So make sure that you don't miss something that is right in front of you. Don't overthink the early questions. They're usually the easiest questions. Rereading questions is a time waster. You don't have time for that. The science is there's really a time crunch on the science. 40 questions, 35 minutes. Read the question one time well. And that means, read it if you want to underline key words and phrases or circle them. I think that's a good idea. But you don't have time to reread questions. All right, doing too many questions. Well, again, the questions get harder in each passage. As you go, your pace needs to be about 9 questions every 10 minutes. So, in order to stay on pace, if you need to guess on the last question or two, go ahead and do it. Not everybody is trying to get a 36 on the ACT. You may know that you are not a strong reader. You may discover in doing practice tests that you can get a better score just by skipping a passage, by doing doing as well as you can on the other passages and skipping one. If you're going to skip one, conflicting viewpoints is a good one to skip. And there's also, you're not going to have time to double check answers. So let things go. keep moving. All right, let's go ahead and take a look at questions here. All right, questions 1 to 6 are based on the following. Let me grab a pen here. It needs to be the right color. A biology student set out to study evolution among rattlesnake populations in the Mojave Desert. The student knows that the 4 primary mechanisms for evolution are, I was going through this, you might want to underline things: genetic drift, natural selection. Now, I can't really do this on the practice test because I'm not writing on the page. I'm writing on the screen, and so I can't scroll and write because it's not, it's, as I say, the notations are not actually on the page. So we can't do that. But okay. The student identified 7 distinct and again, I think I'd underline that: 7 distinct rattlesnake populations. Define their territories, and this map is in Figure 1. All right, don't spend too much time on that right now. The map. Physical characteristics. This physical characteristics, that's given in Table 1. All right. Again, be aware that it's there, but you don't have any context yet with which to interpret any of this until you see the questions. Experiment 2. We have to keep going a little farther because I see the first question is based on Figure 4, and we haven't even gotten to Figure 2 yet. Having gathered this, the student sought to identify the mechanisms of evolutionary divergence. After comparing his results from historical data, the student identified human activity as the primary selective pressure. All right, human activity. Okay. The research materials gathered by the student are shown in Figures 2, 3, 4, and 5. So what we have here is the population. The Mojave Desert from 1850 to 2000 seems to have gone up in the last 50 years here. Figure 3, total precipitation from 1880 to 2010. The thing that jumps out at me here is that it is all over the place. There's no consistent pattern to that. Phylogenetically distinct rattlesnake populations. I think we already covered that there are now 7. As of 1860, there were 2. And finally, the estimated total rattlesnake population, which seems to be dropping off pretty dramatically. All right. So let's try a question based on Figure 4. The number of phylogenetically distinct rattlesnake populations of the Mojave increased by how many species between 1880 and 1970? Well, 1880, it's written in here somewhere. So in 1880, there's 2. In 1970 is right around here. There's 5. So it increased by 3. Right, I like that. It starts off with an easy question. According to Figure 1, which of the following geographic characteristics has the least impact on rattlesnake phenotypic divergence? Human population density, which is what? These dots here. Mountains, high elevation, that's the triangles. Major highway, that's the solid lines, and state line, which is the dotted line. Now, where are the populations? Populations. All right, so we have A and B, which are separated by mountains. We have C, D, again, separated by mountains. G separated by mountains. F. Well, population density, well, you know what? Looking at these, um, they are all falling like on major highways. Um, the thing is, I don't see anything happening across the state line. Population B goes right across the state line. Um, Anything else? I think that's about it. It looks like all the others are factors. And anyway, snakes don't know where the state line. Snakes don't know where the state line is. They're not reading the signs. They're like, welcome to Nevada or something like that. So the answer doesn't even really make sense. So let's go with D. All right. Based on the trends in Figure 5, a scientist could reasonably expect that the total population of rattlesnakes in the Mojave to be approximately what by the year 2030? Here's Figure 5. All right, so it's dropping. It's dropping, all right? It's the last data point we have here is at 2000, but if you follow this trend here, out to 2030 or so, it's going to be 1,000. I mean, I feel like I want to say more about that, but it's just it's not going up. It's going down. We have a data point at 2,000. So forget 3,000, forget 4,000. In fact, forget 2,000 because there is nothing to suggest that it is going to flatten out. It's just going to keep going down. What data gathered by the student in experiment 2 appears to have the least statistical relevance to understanding the causes of rattlesnake evolution? Okay, we got this one. I mean, Mojave Desert permanent residency. Where is that? Yes. Okay, well, there's a definite trend to that. It seems to be, inverse. Well, wait. The causes of rattlesnake evolution. Actually, as that went up, the number of distinct populations also went up. So that does seem to be correlated. Total precipitation. This is going to be the right answer because there's no trend there at all. Phylogenetically distinct rattlesnake populations. I mean, that's kind of in rattlesnake evolution. That's what rattlesnake evolution is. And estimated total rattlesnake population. Well, I mean, it's inversely correlated, but it's correlated. So it's going to be total precipitation because it's all over the place. Based on experiment 1, if a mining operation caused the complete removal of one of the mountains between populations A and B, what mechanism for evolution would most likely increase as a result? Okay, well, it's going to be B. So we're taking out mountains between A and B. All right. And then there was okay, random mutation. Random mutation can happen with or without mountains. Genetic drift, which is just chance events, natural selection. Well, the natural selection, that is, because of the mountains. But if you took the mountains out, took a mountain out, then you could get gene flow between neighboring populations. Based on the student's conclusion in experiment 2, I mean, the conclusion was just that human habitation, okay. Human activity. All right. Yeah. And the data in Table 1, what are the most likely survival mechanisms that snakes consistently developed in response to elevated concentrations of human habitation? And here we have the populations, A, B, C, D, E, F, G. Which are the ones where there is more human habitation? We have A, we have C, we have E, and we have F. A, C, E, and F. So that's what we want to look at. A, C, E, and F. A, C, E, F. All right, what I'm seeing here is, well, all right, first of all, gray coloration. A, C, E, F. No, see, that's not gray. Well, actually, let's just start here. No audible rattle. A, C, E, F. Yes, that fits. Reduced length. These are the smallest snakes, 53, 25, 30, 42. The others are bigger, 84, 83, 67. So what it looks like is the snakes in populated areas have no audible rattle and reduced length. All right. Passage 2. Okay, I like to, first of all, let's look at what we have here. Figure 1 is a condensate. Well, I'm not quite sure what that is yet. Figure 2, figure 2. I think we may have to do some reading here. All right. Like terrestrial planets, gas giants form via condensation. Again, don't get bogged down in the terminology. You can come back to it if it's important, but you want to read just enough so so you can make sense of the graphics. Okay, for condensation and accretion surrounding a star, being far enough away from the star for low melting points to condense, physical collision, coagulation, ices over several 10 million years. Holy cow, hold on. Being far enough away from the star for low melting point elements to condense, the physical collision and coagulation of dust particle-sized ices over several 10 million years lead to the formation of planetesimal bodies, roughly 1 kilometer in diameter. Further collisions between planetesimals instigate a runaway accretion phase in which larger bodies grow preferentially at an accelerated rate. Accretion slows when the diameter, okay. Let's just look at the question here that's right in front of us. A newly discovered planetary body in the solar system has a diameter of 50 kilometers. Okay, so what it's saying is, what are the 3 phases? Condensation. Okay, here we go. A diameter of 50 kilometers. Okay, good. That's right here. What phase is it in? Well, if you're down at 0 to 1, you're in the condensation phase. If you're between 1 and 1,000, which 50 is, you are in the runaway accretion phase. All right, let's go with that. Good. All right, I'm going to keep moving ahead here until I get to another question where we have to read something else. Given the information in Table 1, If the radius of a planet were doubled during the oligarchic accretion phase, by what factor would the rate of accretion increase? All right, so here we have the rate of accretion relative to the radius. It's right here. In the oligarchic accretion phase, the rate of accretion is relative to the radius squared. So if you double the radius, that would be a factor of 2. Then 2 squared is 4. And that would, that's the factor by which the rate of accretion would increase. Okay. According to theory 1. Okay, so now we might have to go back and read a little bit here. All right. Well, this is a little bit tricky here, but what force is mainly responsible? Now, note that runaway accretion and oligarchic accretion are phases, right? Does it say that here? Phase. They're not forces, they're phases. Sort of sounds the same, but it's not the same. It says it up here too, runaway accretion phase. So we need some kind of force. Gravitationally dominant. Okay, so the larger bodies continue to grow because they are gravitationally dominant. So what it sounds like is that what we want is gravity. All right. I don't really like that question. It's just, well, kind of relies a little bit too much on wordplay, but okay. Next. So it looks like we're going to have to go down at this point and do a little bit of reading in theory 2. Okay, so the core accretion does not elucidate the formation of gas giants. The core accretion does not elucidate the formation of gas giants like Saturn and Jupiter. Similar bodies form even within relatively low density nebular disks where random particle collisions are infrequent. Furthermore, Jupiter's solid core is now known to be less than 3 Earth masses, could not, within the lifespan of a nebular disk, have possessed a gravitational field strong enough in its nascent state to gather the existing gaseous exterior by accretion alone, while the comparatively small cores of gas giants may arise by accretion. Okay. And now in this one we have gravitational instabilities. The first one we didn't have that. We had gravitational dominance. So knock off D there. That's not right. Let's see. Comparatively small cores of gas giants may arise by accretion. That's okay. I mean, it looks like they're both talking about accretion, proportional relationships of protoplanet mass, radius, and rate of accretion. Oh, okay. So that is this one here where they're talking about the proportional relationships of rate of accretion to mass and radius. That is theory 1. So eliminate that one. Now we're down to A and B. Equal distribution of high density gas in orbit around a nascent star. Gas giants form via condensation and accretion of gaseous nebular disks surrounding a nascent star. All right. Does 2 talk about that? Anything in here about a nascent star? That's a tough one. I'm going to go with accretion. It looks like it looks like both of them will agree on yeah, small cores arising by accretion. This one is actually all about accretion. So yeah, let's go with solid cores by random accretion. Okay. Let me see the explanation for that. B is not discussed. I think B was discussed. C is theory 1, D is theory 2. Theory 1 states that in the first sentence. It's not a very good explanation. Gas giants form via condensation and accretion of I guess, okay. All right, let's go with it. What primary flaw does theory 2 suggest as evidence against theory 1? Core accretion does not elucidate the formation of gas giants like Saturn and Jupiter, as similar bodies form even within relatively low density nebular disks. All right, well, it seems like they've just come out and said it there, that the formation of gas giants in low density nebular disks, that the core accretion, which would be this up here, doesn't explain the formation of gas giants like Saturn and Jupiter. Okay. I'm going to go with that then. Formation of gas giants in low density nebular disks. Okay. Given the farther positions of the gas giants in the solar system from the sun relative to the closer positions of the terrestrial planets, what would we most likely find as the primary elemental components of the solid planetary cores? All right, so we got to read the question carefully, and I guess this sort of, you know, most of the science questions don't really require much knowledge other than the most basic science. But this one, okay, so what is important here? The gas giants are farther away, Saturn, Jupiter. They're further away than what we're calling the terrestrial planets like Earth, Mars, Venus. Primary elemental components of the solid planetary cores. All right. Higher atomic numbered elements. Well, higher atomic numbered elements, well, let's say it this way. Lower atomic number elements like oxygen and hydrogen, if they're closer to the sun, they're going to be they're not going to be in solid form. It's too hot. So they're going to be in gas form. So yeah, solid planetary cores. It's the lower atomic numbered elements would be more solid the further away that you get from the sun. So it looks like that's what we have here. Lower atomic numbered elements in the gas giants. Those are the solid planetary cores. What are the other possibility? Lower atomic number in the terrestrial, higher atomic number in the gas. No, it's the opposite. Lower in the cores of both. No. Higher atomic in the cores of both. No. That's the difference there. Okay. Which of the following discoveries, if true, would most provide the strongest evidence against theory 2? Star system in a neighboring galaxy featuring gas giants with solid cores. Well, no, I don't think so, because theory 2 says that is part of the theory 2. That is part of the theory 2. Or what am I trying to say? That is part of theory 2, that gas giants would have a solid core. So no. Conclusive proof that gas giants Neptune and Uranus formed via runaway and oligarchic accretion. It's not bad. I mean, it doesn't account for Saturn and Jupiter, but it would be evidence against the theory. I mean, it's the strongest evidence. Well, let's see. An improved computer model that disallows the sustained existence of gravitational instabilities around a nascent star. Well, okay. Larger gas components. Okay, so the small cores may arise by accretion, but the larger components are the result of gravitational instabilities. Okay. Well, if there's no gravitational instabilities, then the theoretical basis of theory 2 is shot. All right, so let's go to D, the absence of evidence for gravitational instabilities in our own solar system. Okay, that's, I mean, that's kind of a red herring there, in that, you know, the fact that there are no gravitational instabilities in our own solar system, these planets formed a long time ago. So we don't need gravitational instabilities now in our own solar system. We needed the gravitational instabilities a long time ago. But if we have a model that said, no, you're not going to have these gravitational instabilities around a nascent star, then the whole theoretical model is gone. Okay, let's see. A physics student sought to better understand the distinction between transverse and longitudinal waves. We probably don't need to read any more of that just yet, but based on figure 1, a transverse wave, where is figure 1? There's a transverse wave. A transverse wave with a crest that is twice the crest of another transverse wave would have, well, okay, so amplitude is the distance from the midpoint to the top or bottom of the wave. So if the crest was twice the crest of another wave, then you would have twice the amplitude. Whoa, 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 whoa. I think I forgot to show the answer. Show answer. Okay. According to the information in figure 4, at what point in an earthquake do seismic waves travel at their highest velocity? Figure 4. All right, so velocity is the velocity is shown across the top. Velocity increases here, and then this point right here, this is the highest velocity, and that is transitioning from outer core to mantle. So yeah, right here, transition from outer core to mantle is the highest velocity. All right, based on figures 1 and 2, an electromagnetic wave, so that would be shown here in figure 2, is best described as 2, phase matched or phase inverted. Well, let's start with that. It looks to me like the electric field, magnetic field, like these are matched. Actually, there's a dotted line you can see from here to here, indicating that they are matched. So let's go with two-phase matched. So now we're down to C and D. Perpendicularly oriented, yes. Transverse or longitudinal? Well, it's not longitudinal. I mean, you can see this a transverse wave. It's like a sine wave. So it's got to be two-phase matched longitudinal waves. Oh, I forgot to check the answer again. Show answer. Uh-oh. Oh, Jesus. All right, I selected a longitudinal by mistake. I meant to select transverse. Transverse. It is definitely a transverse wave. All right, we'll pretend that didn't happen. Next. Based on figure 4. Figure 4. Okay. Okay. A seismograph placed on the surface of the Earth directly above an earthquake that has at ground zero 410 kilometers underneath the Earth would first detect the quake after approximately how much time had elapsed? Okay, so I think the mistake to avoid here is looking at this as though this represents elapsed time, which it doesn't. This is just showing a velocity. So one thing that we can see from this is that the P waves move faster. And so the P waves are going to be the first detected. So if a P wave is moving, and we're going to say 410 kilometers under the Earth, it's moving at about 8 kilometers per second. So to reach the surface, 410 kilometers at 8 kilometers per second is going to be 50 seconds. Light can travel through outer space, but sound cannot. This is most likely because space is a vacuum and sound is a longitudinal wave that relies on the movement of particles for propagation. Well, hold on a second. Where do we see a sound wave here? Oh, I see. Figure 3 illustrates a sound wave. Okay, so sound is a longitudinal wave. It is not a transverse wave. So, all right, right away, I'm going to eliminate C because sound is not a transverse wave. B and D are pretty similar. Well, you know what? D actually doesn't even make sense. A frequency. I mean, a longitudinal wave doesn't have a frequency. Uh, a wave, a transverse wave would have a frequency. So I'm going to eliminate D. Sound travels at a much lower velocity than light. I didn't see anything in here that says that, I mean, it does travel at a lower velocity than light, but let's see. But I don't see that in here, that it travels at a much lower velocity than light. I'm not sure that is, I'm not sure that that's the case. What is this one again? Space is a vacuum. Sound relies on the movement of particles for propagation. That's the one that makes the most sense to me. We're talking about propagation here. Yeah, we're down to A and B. I don't know that longitudinal waves travel at a lower velocity than light, and I'm going to go with A. Right. All right, new topic. Student first studied 5 morphological aspects of 5 frog species. Then, using fossil remains, student estimated the degree to which the modern frogs are related, as well as which traits are derived and which are ancestral. All right, summarized her findings in Table 1. So we have a table of frog, what can we call that? What are they calling it? Traits, 5 frog traits. And we have, what is figure 1? And we have an evolutionary tree. All right, since the first question is on table 1, let's just go with, let's go ahead with it. According to table 1, which of the following frog species would not have a visible tympanum, which is a hearing organ? So the tympanum, the column is here, and if we go down, that's the fossil remains, so we're not interested in that. The others, well, this one is internal, so that is not going to have a visible tympanum. All right, the next question is just reading a table. Let's go ahead with it. According to Table 2, which of the following nucleotides of DNA is not to be found in locus 2 of any frog species? And we have 4 of them there. These are usually abbreviated ACGT. Locus 2. I see A's, G's, and T's. I do not see any C's. So let's go with cytosine. Based on the results of experiment 2, the student changed her evolutionary tree model so that which 2 frog species were no longer as closely related. Okay, there's a description of experiment 2 here, but I don't think we need to. I don't think we need the description to compare the tree models. So here's the evolutionary tree model for experiment 1. This is experiment 2. Which 2 frog species were no longer as closely related? And we have pipiens and aurora, which they're not as close. Well, they're not really related here anyway, so let's skip that one for now. Caddisbia something, a true eye. Again, those are not really connected either. Pipiens and casts something. Now those are related here. So let's look at the next one. And okay, so the next one, they're separated. So they are not as closely related in 2 as they were in 1. Okay. Based on table 2, which locus is most likely to contribute to a lack of complete correlation between our aurora and the assumed ancestral species? I have to get a little more information on that. Okay, so she determined that A true I is the closest morphological relative to the ancestral species, so that is going to be the outgroup against which to compare the other 3 species. Okay, so the outgroup. Okay, so we can consider this to be like the ancestral species, the outgroup. And which locuses contribute to a lack of correlation. All right, let's try locus 1. Compared to the outgroup, R aurora and the outgroup, AACT, GAGCT, that's exactly the same. So it's not 1, and all the answers have 1, except this. It has to be this. I mean, those don't correlate exactly, I hope. That one doesn't. This one also doesn't, so let's go with that. All right, using the results of experiment 1, a common ancestor between L. pipiens and L. something would most likely share both of the following characteristics. Okay, so experiment 1, let's go back to experiment 1 and see what they have in common. That would be this one, pipiens, and this one, which I can't pronounce. Similarly, okay, so the first one, lateral, so eye orientation, yes. This one, no. This one, not really. This one, not really. This one, yes. What is that one? Adult terminal vertebrae. So eye orientation, adult terminal vertebrae. Let's go with that. They are identical in both of those species. Archaeologist discovers a frog that he wishes to categorize as either an ancient ancestral species or a modern descendant species. Which characteristic of the frog's remains would be most helpful in making a definitive determination? All right, so that means we've got to look at the fossil remains and see where do we have a difference between the fossil remains and the modern descendant species. Eye orientational lateral is not distinctive based on these, what is this, fold length? We have none, none, that's not going to help. This one we already saw, we had internal and internal. This one we have full webbing. This one we have prominent tail. This is the only one with a prominent tail. These other ones have some things that I don't really understand. A small tail, yeah, I don't really see frogs with prominent tails. So it looks like the length of the tail is going to be the distinguishing characteristic. Okay, a new topic. Allotropy is the ability of some pure elements to exist in different forms within the same phase of matter. All right, so let's kind of process that a little bit. So we're talking about elements, and they exist in different forms within the same phase. Okay, so matter can have 3 phases. Wait a minute, let me see the phase diagram for carbon here. What is that? Temperature, phases. Okay, so yeah, I mean, you can see with the phases of car, okay, D is a liquid, E, vapor, that would be a gas. Diamond, that's a solid. So for phases, we're talking about um, liquid, gas, and solid. All right, so I think I kind of understand what that is. And in fact, the first question deals with that. Which of the following can be described as allotropes? The first one, you have a solid and a gas. So I'm ruling that out. B, dioxygen gas and ozone. Well, ozone is oxygen. I think ozone is O3, right? They're both gases. They're both oxygens. That sounds like the right answer. Sandstone and quartz. Those are not elements. Uranium and plutonium are elements, not the, okay. Yeah, I gotta back up there. Sandstone and quartz. Okay. They're multi elements. They're not elements. And D, uranium and plutonium. Okay, those are both elements, and I guess both solids, but they're not the same element. So the only one that works here, according to the definition, is B. Where's the show? Yeah, okay, good. Sublimation is the phase transition of a solid directly into a gas. According to figure 3, under which of the following conditions might sublimation occur for carbon? All right, well, let's take a look here. Did we already look at this? Yeah, so a gas form here is E, vapor. That is right here. F is a liquid. And what is this? This looks like A. What is A? Diamond and metastable. Okay, so that's a solid directly into a gas right there is what it looks like. Where is that happening? That is happening at a pressure of 0.01. Temperature here is it's about 4.5 times 10 to the third. So that's this one right here, 0.01 and then 4,500. Based on figure 3, what form of carbon is capable of becoming a solid, liquid, or gas with relatively minor alterations to temperature and pressure? Well, okay, wouldn't it already have to be a solid, liquid, or gas? Maybe it's talking about becoming some other form of liquid. All right, the only gas that I see on here again is the F. I'm sorry, E. So it's got to be somewhere around E. This is a solid. A is a solid. E is a gas. F is a liquid. Now, what is D? Okay, so D is liquid carbon. Now, it looks like liquid carbon could go to a solid, that's A. It could go to metastable liquid. It could go to vapor. I mean, that's the only one that I can see here where we've got a solid, a liquid, and a gas. They're all right together here, and the only other thing in the area is D, liquid carbon. So I am going to go with oh, wait a minute. Whoa. Yeah, metastable liquid. Oh, okay. Whoa, wait a second. Um, well, I don't know what, yeah, I don't know what else to call it. I guess you could go, okay, I guess you could go the other way and say the metastable liquid could go from, could also go to a gas, a solid, and liquid carbon, but that still doesn't change the answer. So I'm going to have to go with that one. Diamond is sometimes described as the hardest naturally occurring carbon allotrope, probably because, let's see, crystalline structure is extremely dense, maybe. Most thermodynamically inert of all the carbon allotropes. I don't even remember seeing anything about that in here. Oh, wait a minute. Thermodynamic stabilities, that's figure 2. It is the most thermodynamically inert. I guess that's true, but I don't see what that has to do with the hardness. So I'm going to put that on hold for now. It has a low molar mass per cell. It's down here somewhere. Actually, it has a high molar mass per cell. So we can definitely eliminate C. It is formed under extremely high pressures. Well, you know, diamonds are formed under extremely high pressures, but it's generally a poor idea to take something that, even if you know it's a true statement, but it is not mentioned in the, it's nowhere in the passage, and just pull that out as the answer. So nowhere does it say here that anything about how these elements are formed. Most thermodynamically inert. I don't know what that has to do with the hard. So let's take a look at the crystalline structure. It's hard to, I mean, it's kind of hard to tell from this. It does, you know, seem to be a more, what should we say, a complex interlocking structure. What if we go down here? Yeah, an isometric okay, whatever. But the density, yeah, it does say the that it is extremely dense. Okay. So we're down to A and B, and I don't see what being thermodynamically inert has to do with hardness. The crystalline structure being extremely dense would seem to be relevant. So I'm going to go with A. Given that the molar mass of carbon is roughly 12 grams per mole, the chemical formula C60 most likely refers to what allotrope? All right, 60. Well, what if we had 60 carbon, what if we had 60 carbon atoms? At 12 grams per mole, 60 times 12, 720 grams per mole. So that's right here, the Buckminster Fullerene, 720 grams per mole. So let's go with that. Is this a new one? It is. All right. Through most of human history, combustion has been among the most significant processes. All right. Produces heat, produces energy. Generalized reaction is this: fuel plus oxygen plus activation energy. Gives us oxides and combustion energy. Heat and energy. Okay. Wood, coal, oil, natural gas, most common fuels. Information is provided in table 1. In order to achieve combustion, I'm going to hold off on that until I have some context for it. Because oxygen absorbs heat, too much oxygen, I want to see what figure 2 is about. However, because oxygen absorbs heat, too much oxygen will deplete the usable energy as illustrated in figure 2. All right. So what are we seeing here? As oxygen increases, the usable energy goes down. That the highest efficiency is right here in the middle. Oxygen going up, efficiency goes down. We've lost the highest efficiency. All right, good. Question is, which of the following fuels from table 1, okay, table 1, would have 1 billion molecules consumed with the least amount of oxygen? Okay, well that's good because it's actually a column right here in the table. Oxygen consumed per fuel molecule. So what we're looking for is the least amount of oxygen consumed. And what we have is this one, methane. According to figure 2, efficiency of combustion increases as the amount of CO does something. All right, so highest efficiency is right here. How do we get there? Well, we get there, here's CO right here, this line. It increases and then it decreases and then we get to highest efficiency. So it increases then decreases. Acid rain is caused by the presence of sulfur dioxide and nitrogen oxide that react with water to produce acidic particles in raindrops. To minimize the possible creation of acid rain, which 2 fuels from table 1 should not be burned. All right, so what we're looking for is we don't want nitrogen oxide, we don't want sulfur dioxide. All right. So here's the oxides produced. This column here, there's nitrogen oxide. Here's sulfur dioxide. All right, so we don't want bituminous coal. Here's nitrogen oxide. Here's sulfur dioxide. We don't want that either. The others do not produce that. So it's the coal, bituminous coal, anthracite coal. Someone wishes to have a fire using all 5 of the fuels from table 1. What would be the best sequence from first to last? All will be successfully ignited and used given that only one type of fuel can be used, and 2, the person starting the fire wishes to do so with the lowest possible amount of heat. All right, so what do we have here as far as the lowest possible amount of heat? Let me think about this. Heat per mass? No, it's okay. We want to ignite it. Heat of combustion, I don't think that's right. Let me see this. Where is that thing again? All right. Okay, fuel, oxygen, activation energy, and that produces the combustion energy. Okay, so that's after ignition. This is after ignition. What I think what we want here is the auto ignition. That how much heat do we need to ignite the fire? Okay, what's the lowest thing on here? Octane. What do we have in the answers? Well, there's really only one that starts with octane. Let's move ahead a little bit and see if we're proceeding in the right direction. Cellulose is 300, yes. Bituminous coal, 450. Yeah, so it looks like this is the right order here. All right. Based on the information in the passage, campers who made a fire outdoors would find which substances in the fire most likely burning the hottest after it has been lit for at least an hour's time. Okay, so this is all wood. Wood on the top of the fire, exposed to a great deal of oxygen. Wood in the middle, accessible. Okay, I see where we're going with this. So they were very clear about the fact that, where is it? Excess oxygen. Okay, yeah, oxygen absorbs heat. Too much oxygen will deplete the usable energy. All right, good. Exposed to a great amount of oxygen. No, that's not what we want. You want it burning the hottest. You don't want a lot of oxygen. Wood in the middle, moderately excessive oxygen. That doesn't sound good. Wood at the bottom, you got a little oxygen, but only enough to keep it burning. That's good. All of it's at the same temperature. No, I think they were very clear about the role of oxygen, and the oxygen is going to reduce heat. All right, questions 35 to 40. Upon learning that light demonstrates the characteristics of both a wave and a particle, a physics student decided to observe the wave behavior of light through a double-slit diffraction experiment. This is a pretty well-known experiment, I think, but I'll be honest and say that it's been a while since I've seen it, so I'm going to have to go with whatever they give me here. Experiment 1. Actually, before we go to experiment 1, because this first question is on experiment 2, and the question is, if a fourth type of colored filter, where is experiment 2? The student is using 3 separate color filters, and we're talking about distance between bands. Distance between bands. All right. If a fourth type of colored filter is tested in experiment 2, resulting in a distance between bands of 0.115 centimeters, the wavelength would most likely be between, all right, so 0.115 it's between the blue and the red. So wavelength is most likely going to be between 5.1 and 6.5 e to the negative 5th centimeters. Just fill in the gap there. Theoretically, based on the information in experiment 2, if only the length between the card and the screen were, wait. If only the length between the card and screen were doubled, and only the wavelength were impacted, the wavelength would be, well, all right, let's take a look at that. We need a little bit more information here. All right, actually, I think I need a pen for this. All right, the length, so n, what is n? N is the diffraction order. I don't think we're interested in that. Lambda is the wavelength. All right. Distance between bands, we are not interested in. Length between the card and screen, we are interested in that. And that is L. What is D? Distance between the slits. So the only thing we're interested in is, let me get a pen here. Okay, the only thing we're interested in is this, which is the wavelength, and this, which is the length between bands. Now, we're going to double I'm sorry, length between the card and the screen. We're going to double the length between the card and the screen. Well, if we do that, it's going to, so this would be times 2. It's going to cut the wavelength in half. So let's go with that. Okay. To the nearest tenth of a second, how long would it have taken for the light to have traveled from the light source to the screen? The light source to the screen. The light source, well, it's just 20, I guess from here to here is 10 meters, here to here is 10 to 20 meters. The thing is, light is really fast. It isn't even possible, as far as we know, to travel faster than the speed of light. So you want light to go 20 meters. It's instantaneous. I mean, I don't say anything in here about doing a computation on it, but you want to round it to the nearest tenth of a second. It's 0. Which of the following changes to experiment 1 would not have narrowed the pattern of repeating bands of light? Not have narrowed the pattern. All right, let's take a look at this. All right, so the order of diffraction represented by n corresponds to the distance between, well, how do I want to say this? Well, the relative width of the pattern. Narrowed the pattern. Okay. Yeah, so n represents the width of the pattern. If we could decrease n, we would decrease the width. We would narrow the pattern of repeating bands. So I'm going to go back to this equation here. Now here's n, and what we want to find is, all right, so n, which would not have narrowed the pattern. So which one of these would not decrease n? Decreasing the distance between the bands, which is x. Now if you decrease that, it is going to decrease n. So that's not what we want, because that would cause that would narrow the pattern. All right, increasing the distance between the slits. Where is that? D. If we decrease D, it is going to decrease N. I'm sorry, I'm still on decrease. I'm sorry, increasing the distance between the slits. If we increase D, it's going to increase N, and that is not going to narrow the pattern. All right, so B looks like the answer provisionally, but let's look at this. Increasing the length between the card and the screen, that is L. If we increase that, the denominator, it's going to decrease N, and we don't want to decrease N. Cannot be determined. No, I think it can be determined. So let's go with B. Which of the following is not an independent variable in experiment 2? Not independent. Okay, filter color. That's independent. We can change that. Wavelength of the light. Wavelength of the light is a dependent variable. It's something that we measure based on That's something we measure as part of the experiment. So provisionally I'm going to say it's B. Slit separation on a distance on the card. That is independent. We can change that if we want to. Distance between the card and the screen. That is independent also. We can change that. The only thing that's not independent is the wavelength. That changes based on the other parameters, and then we measure that as a dependent variable. So let's go wavelength. Okay. Final question. Student conducted a third experiment that was just like experiment 1. Okay. Except he used a material that would shift color if it absorbed light. Okay. Results were identical to those of experiment 2, except that the material remained a different color after the light source was turned off. Results of this third experiment would serve as the best evidence to a physicist who was a member of what theoretical school about the who was a member of what theoretical school about the nature of light? All right, so it's definitely, well, what are the answers here? Only a wave, only a particle, both a wave and a particle, or neither. All right, well, it's definitely a wave because they talk about the wave, wait a minute. Okay. Upon learning that light demonstrates the characteristics of both a wave and a particle. All right. I feel like they're kind of giving us the answer there, but they're talking about wave behavior throughout this. All right. The wave behavior of light, blah, blah, blah. Something about wave. Diffraction is a wave interference phenomenon. Okay. So it's a wave. We're talking down here. We're talking about wavelengths. However, if the material remains a different color after the light source is turned off, then that's got to be happening through some sort of particle absorption, right? It hits it and it stays there. So I'm going to go wave and particle. Doesn't it give the answer away right here? Upon learning that light has the characteristics of both a wave and a particle. All right, let's go with it. All right, that is number 40. We're going to submit this. I don't think anything happens when we submit it. I don't think we get a score or anything. Writing, optional. Okay, we're not going to do writing, but I hope you enjoyed the science video. Please feel free to, well, you know what? I'm just going to say we'll see you next time.